Okay, let's continue with our drop jump analysis. And we are picking up from the last video where I talked about identifying initial velocity at contact from the height of the box. All right, you just do that calculation. And it's wrought with errors, of course, and confounding factors. But that's why when you collect data on a drop jump, you try to be really careful about instructions to subjects. Okay, so now I want to generate kinematic data from kinetics. Give myself a little room here. All right, so I'm going to draw 4 plots. The bottom plot is the ground reaction force, and I'm just going to do vertical. I'll do time. Right above that, I'm going to put acceleration versus time. Right above that, I will put velocity versus time. And right above that, I'll put position. Always label your axes. Always give your axis units. Oh, I should have done that. Meters per second squared, newtons. Okay. Always line up your time axes. So vertically, so that the time is all synchronized. Time 0 is the same on all these plots. And you notice I drew this one different than the others. That's because I'm not going to go into negative positions. However, when I do this in MATLAB, I often start the position plot at position 0. And so then I will end up in MATLAB with some negative positions, meaning that the 0 represents the height of the center of mass while standing. Okay, so I do it a little bit differently in MATLAB versus on this sketch, but the pattern will be the same. The meaning of the pattern will be the same. All right, so remember, we're only dealing with the data from the moment we have contact to the moment we have takeoff. We don't know anything else outside of these 2 moments in time for our data. And I know I drew the ground reaction force a little differently for the last video, but I'm going to just draw it like that. I'm going to skip the little impact peak here just to keep it simple. All right, so that's our roughly a typical ground reaction force for drop jump. What do we do now? Well, I better pull out another piece of paper, otherwise this one gets really messy. Kinetic analysis, identify all forces acting on the object. And in this case, our object is a person in contact with the ground. Oops, I messed up. All right. All right. Okay, well, good enough. All right, just big feet. What forces are acting on the person? The ground reaction force and the force due to gravity pulling on the person. What do we do in a kinetic analysis? We add up all the forces acting on the object and we understand that object's acceleration, specifically the center mass acceleration. The forces we have acting on the person, Fz is up, gravity is down. So we get that. Or we can rewrite this a couple different ways. I can do Fz equals MACOM plus body weight. Or I can rewrite this as acceleration at center mass is equal to Fz minus Fg body weight divided by mass of the person. Super easy to get kinematics when we know all the forces acting on the object. And in this case, we do. There's 2 forces acting on the object, and we've got them in the numerator. We know the mass of the person, and therefore we can figure out the center mass of the person. All right, so let's come back over here. I'll draw a dotted line roughly to represent body weight, roughly. All right, so what are we going to do? We're going to generate our acceleration profile using this equation, ACOM equals FZ minus FG divided by M. It's that simple. We subtract body weight from every data point, and what do we get? We get a curve that looks just like the ground reaction force curve. My sketch. I'm going to come down there a little further. That is body weight. That's this part above here should be the same as that. These parts should be the same as that. Because when the ground reaction force is less than body weight, Fz minus body weight, when this is less than that, this will be negative. Acceleration will be negative. When Fz is greater than body weight, it's above this dotted line, greater than body weight, this numerator will be positive. M is always going to be positive, therefore acceleration is positive. And again, over here, Fz is below body weight. The numerator will be negative, acceleration will be negative. Okay, so these two these are easy to determine from each other. Okay, so now we've got acceleration, we understand that, and now we want to generate the velocity profile. How do we do that? Well, we're going to integrate this data set, and we're going to generate our velocity profile. And we would calculate the area under this curve. And that area under this curve will tell us the change in velocity. Remember, A equals delta V over delta T. Or I can rearrange this as delta V equals A delta T. This is what I've explained in the other videos. This is the area under this curve, base times height. All right. So if I drew, a box like this, I'm exaggerating. This would be the base, delta t, and this would be the height, A. Now, remember I did another video on using a rectangle versus a trapezoid. Either way, okay. At the end of the day, it's still solvable for the area under that curve, all right, based on that. But this area under the curve is giving us the change in velocity. It's not giving us velocity, it's giving us the change in velocity. So all I know up here is the change in velocity based upon this product. Now, if I take this acceleration right here, that's a negative acceleration. Knowing my math, what that tells me is the slope of the velocity versus time plot has to be negative. Has to be negative. Has to be, okay? In order for acceleration to be negative, Vf minus Vi, that change has to be negative. So final velocity minus initial velocity. That difference needs to be negative. Well, how do I get a negative acceleration? I have to have a negative slope here. I'm just going to draw one, okay? I've got that one. What does that slope indicate there? This is all positive velocities. This would be slowing down, moving upwards. Is that going to be that slope? Well, that's a negative slope. That's going to give me a negative acceleration. That's what is going on here during the drop jump? Obviously not, because here, this is contact, this is contact, this is contact, this is contact. At this point, we know at the moment, let's jump up here, we know what's going on with position. The person center mass, they touch down, then they go down, and then back up. And then they're off into the air again. And prior to this, they're in the air as well. We know that. We know they're going downward. This is actually saying they're going upward, but this matches that. That is a negative acceleration, all right? But that's not the right velocity. Well, maybe I'll draw another one. Oh, that's still negative acceleration. That's still slowing down, moving upwards. That doesn't work either. No, no. Well, what about that? That's a negative acceleration. That's a negative acceleration. Now we have speeding up, moving downwards, okay? And it turns out that this is what ultimately we want to work towards. Well, how do I know it would be this speeding up, moving downwards? I'm exaggerating here, but that's okay. Speeding up, moving downwards. Well, I need to know this initial velocity. And if I tell you that the initial velocity at contact is some negative value, it doesn't matter what it is, 1 meter per second. Now I can tell you exactly what's happening with velocity because I'm calculating the change in velocity from integrating the acceleration versus time plot. And I know that that change for this region is going to be negative. That means my slope is going to be negative. Now I can know exactly what that slope is, and I can fill it in starting at that velocity point. And then I would continue this on, and I would calculate this next area, which is going to be positive. All right, but now I'm right here. And now I'm going to go positive velocity, or excuse me, positive slope. I'm going to go positive slope all the way up until here. Well, actually, I'm going to go all the way through there. This is all positive slope too. And then I'm going to hit a negative slope right here again. And then I'm off into the air. Oh, I'm exaggerating. Okay. So I can put a little curvature into this. It's a little bit more curvature. It's not straight lines. If it was straight line, acceleration would be constant. But it's just sketchy. Oh, well, now I'm messing up my sketch, but that's okay. So I am able to integrate this acceleration profile to yield my velocity profile when I know VI. If I don't know that initial velocity, all bets are off in terms of what I can do, because I actually can draw any parallel line to this, and all of those parallel lines will give me that acceleration profile exactly, okay? But they all have different interpretations. For example, this velocity profile is all positive. That would be all upwards movements. And I could do one down here. This is all negative velocities. Those are all downward movements. So they don't make sense for the drop jump. And why don't they make sense? Because we don't know what the initial velocity is. The mistake a lot of people will make is they integrate the drop jump and they'll start at zero velocity at contact. That's incorrect because velocity is not zero at the moment of contact. Velocity has to be moving downwards because you're landing from a jump. Okay, so that's how you integrate the acceleration profile, and then you do the same thing to integrate the same process of integrating the velocity to yield the change in position, or the change in position is equal to V delta T. And now again, I'm at, I'll draw it over here. Here's my rectangle. V is the height of that rectangle. Delta T is my sample rate. And I calculate the area of that rectangle. That tells me the change in displacement. So again, you need to know some displacement. But in this case, a lot of times what I do in MATLAB is I just start that initial displacement, my initial position as zero, and zero being the height of the center mass at the moment of contact. And then they go below zero, going down, and then come back up towards zero, and then sometimes even leave the ground either lower or above that zero value. Okay, now that's all sketching. I need to put this in motion and write some MATLAB code and show you how to do this in MATLAB. And I'll do that in a separate video. Okay, thanks.